in math, constraints are actually good. They give you more information to work with and make equations perhaps easier to solve oftentimes. So in our case, we've run into a possible problem that actually turns out to help us in the end. So let's look at L squared acting on the state f. It's Lx squared plus Ly squared acting on the state f plus Lz squared acting on the state f. And that's just Lx squared Ly squared f plus... We're going to change formulas. Instead of just using m, I'm going to use mh bar for eigenstates of, or eigenvalues of Lz. M squared h bar squared f equals lambda f. You can keep applying the raising operator to f repeatedly, and it'll give you each time a new state with higher and higher values of m. But the lambda does not change. So theoretically there would come a point where you'd apply the raising operator to f so many times that our Lz would be higher than the total angular momentum, which would be nonsensical. So we're going to propose that our Lz has a maximum value of LH bar. In the state F max, which is an eigenstate as per usual of Lz with total angular momentum lambda. Well, due to our probability interpretation, the state with Lz higher than LH bar is A plus acting on F max, and it should have 0 probability. Well, our states are probability amplitudes, so we need our state with Lz greater than LH bar to be 0. So we have this equation here. Now let's look at this equation again. We can write, let's look at A, the lowering operator acting on the raising operator. This is equal to Lx minus ILy on Lx plus ILy. And the order, remember these are operators, so the order that you do them in is important. Lx squared minus Ly Lx plus I Lx Ly plus I times negative I plus Ly squared equals Lx squared plus Ly squared, rearranging the terms, plus I times the commutator of Lx with Ly. Well, that's just L squared minus Lz squared, and that's just I times IH bar Lz with our commutation relations. So we can rewrite our L squared by adding these terms on. That's just negative I times I is negative 1. I'm A minus A plus Lz squared plus HLZ L squared is equal to this. Now let's act it on F max. L squared F max equals lambda F max, since our total angular momentum eigenvalue does not change. But we know that A plus acting on F max is just 0. And we know that F max has LZ of LH bar. So this is just H bar squared L squared plus H bar squared L on F max. And this gives us a constraint. Lambda is equal to H bar squared L plus 1. So that means if you have a defined total angular momentum, it determines what your maximum L sub z will be. We can use a similar argument for the lowest eigenvalue of L sub z. Theoretically, you could keep lowering F as well until your LZ would become, the absolute value of your LZ would be rather large still, because you keep subtracting off H bar so many times. But because this is squared, the negative sign will vanish and this will still be a positive number, and it still has the potential to be more than our lambda. So we're going to do a similar argument where we define F min is equal to 0, the state acts on, or the lowering operator acts on F min, and you get 0. And we'll say that our LZ eigenvalue with our lowest LZ eigenvalue is in H bar. Similarly, let's look at the raising operator working on the lowering operator. And that's just Lx plus ILy, Lx minus Ly, equals Lx squared plus Ly squared minus the commutator of Lx with Ly, which is equal to L squared minus Lz squared minus plus, it's a opposite sign, H bar Lz. And it acts on, so we can rewrite L squared as Lz squared minus HLz plus A minus. So let's act it on F min. Well, that's just 0 by definition. And that's just n squared H bar squared minus n equals lambda. So lambda not only determines our lowest possible LZ eigenvalue, but it also determines our highest LZ eigenvalue. And note that L must be greater than N. So let's say that, well, these have to be equivalent to each other. So let's say that N is equal to some A times L plus B. And that's just N times N minus 1. So AL plus B squared minus AL minus B must equal L squared plus L. A squared L squared plus 2 ABL plus B squared minus B 2B minus 1 times A must equal L squared plus L. Well, A squared must equal 1 and B squared must equal B because there's no constant at the end. And 2b minus 1 times a is equal to 1. So let's look at the solution where a is equal to negative 1. Equals negative 1, then b must equal 0. And this has two solutions, b equals 0 and b equals 1. So this one is with a equals -1. And let's look at the other solution, a equals 1. 2b minus 1 equals 1, and b equals 1. So a equals 1 is paired with b equals 1. So there's two solutions. N can either equal -L, or n can equal L plus 1. But we already said that n must be less than L, so that solution is nonsensical. So we must have that n is equal to -L. So, in summary, our total angular momentum lambda determines L, and our LZ eigenvalues are between L, or -L, and L, which means, and it goes in integer steps since the raising and lowering operators add a factor of h bar, or add 1 to it each time, which means that if you have lambda, for every eigenvalue lambda, there's 2 L plus 1 possible states, so it's 2 L plus 1 fold degenerate. Our LZ eigenvalues go up in integer values, where mh bar is equal to our LZ eigenvalue. Then L minus -L equals 2L must be an integer, meaning that L can either be integer or half integer. If we had used the spherical coordinates version and actually used the physical operators instead of just analyzing it, we would have found out that L would only be restricted to integers.